let's get started. Hello, how are you? Everything is fine? Yeah, I'm fine too. And today we are going to understand about quantum wave functions and deriving Schrodinger equations. So maybe you understand that okay, in quantum mechanics we have wave function and we have Schrodinger equation that is basically tell you that what is the dynamics of the quantum wave function is. But the question again starts that I want to learn quantum mechanics, but everyone says that quantum mechanics is kind of too weird to understand, it's too difficult, and it's completely different from classical mechanics. So I'm taking different route. Why I'm taking different route? Because when I was learning and when I was first heard of quantum mechanics, and the way I learned, the way I taught by professors is kind of root thing. Somebody use history, that okay, how historical ways, what is the history behind the evolution of quantum mechanics, because the theory has not built in a one day. It took around many years to develop, right? And there are a lot of experiments going on, and professors in the college will going to teach you those historical things, and how there are classes between the classical and classical description of the particle and so on. And hence a Schrodinger guy came and he proposed something very weird, that okay, a quantum particle cannot be considered as a particle, it has some wave function and so on. And then they will give you something that okay, these are the definitions you have to understand, these are so and so and so and so on, all these things, all this blah blah blah. But again, if you will left with the approach is something what like artificial, right? Why it feels artificial, that they will going to actually dictate you some kind of rules, that okay, this is the thing that you have to follow. And then we are going to live with class, or the semester is over, and again you even don't understand fully that okay, there will be quantum mechanics, and why should I even care about the quantum mechanics, right? So yeah, you may get interested at, oh my god, quantum particle can tunnel through here and there and then. But the question that arises in our back of our mind, that okay, well, we have learned the quantum mechanics, how does it operate, and we can even solve the problems. But the problem is that, let us say that I want to become a scientist, or I have become a scientist. Then obviously I want to develop my own theory. Then how can I, if I were to be a scientist, how can I make my own different theory? For instance, you know that general relativity that was devised by Einstein, and the quantum mechanics by Schrodinger and many more scientists. And these two theories are actually have a different path, right? Have a different path, and they are evolving differently, and they are not many. They are not, they are having a very different descriptions, and you have already heard of by many popular lectures that they cannot be merged. Now you say that okay, my goal is in this lifetime that I want to create my own theory that can quantify the quantum mechanics as well as the general relativity. Now the question is that okay, let's say that I am a scientist, and I am kind of in era between 1900. I know Einstein, I know, let us say, something. But in that moment, how do I know that I have to propose this wave function? Or let's say that I want to solve many different problems in physics, which is again unsolvable, yet not solved by any scientist. Then how I'm going to develop my theory? And this was my question too, that okay, you have tell me very various things, that okay, these are the operators, this is something, this is blah 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 blah. And the question is that okay, since I am not a scientist, therefore I don't know, because I have to just suck all this thing, whatever somebody will feed me, that okay, these are the rules and so on. But the naturalness is absent. Professors actually take different routes. Let's say that okay, you have seen the photons have dual characteristics, and they are telling you very different experiments, let's say Young's double slit experiment and so on, and they are giving you like that, okay fine, they are actually giving you some motivation, okay, this is the way you have to. But they are actually forgetting that okay, somebody is there who in future would want to work out their own theory, then how he can develop his own theory. And that is the one question, is that how a theoretical physicist think. Let us say I want to become a theoretical physicist. How can I do this research? How can I develop my own idea? Now I'm going to take a very different route in this understanding this wave function and Schrodinger equation, because I am assuming that okay, I have very good understanding of classical mechanics, but I don't know anything. I don't know nothing about quantum mechanics, right? And I want to, with some information, I am not going to take any information from the experiments. I will take some of only 2 or 3 experiment to actually derive this Schrodinger equation and derive that okay, how quantum wave function is actually emerging with these definitions and so on, right? So my approach is from the theoretical physicist idea. I am a theoretical physicist and I want to understand about quantum mechanics and Schrodinger equations. I want to devise my own theory to actually figure out the behavior of quantum particles. So please see this video till the end, because we are going to understand a lot of things in this video. Okay, so let's say that I have very good understanding of classical mechanics, right? And if I am a very good understanding of classical mechanics, so let us say that if you will throw me a ball, I will say that okay, if you are throw me a ball, let us say it is a particle, right? A ball is a particle and dimension like is a point mass particle, right? Obviously, let's say that it will have some velocity, and okay, I cannot just simply consider that okay, there is some kind of empty space. I will say that okay, let's say that where I can, first of all, I will say that okay, if you have this particle and having velocity, what would be its location? So my first question would be what would be its location, and the location can be found out by placing a coordinate system. Over here it is 0 0 and this is x and y. You see, when I speak about the location, I must use the reference point. In space, where is this particle? The particle could be anywhere, but give me some location. Similarly, I can define the velocity. In order to define the velocity, I have to also take in which reference? This velocity in the moving frame, that okay, this frame is moving with some velocity, or it's in rest, right? So these are very relative quantities, understand? And then I want to have some kind of clock attached to it, that yeah, this is the clock of this mass m particle, and the velocity is not the very high velocity. It is not a speed of light. It is very, very less than speed of light. Let us just see. So we understand that we are working with a non-relativistic limit, correct? Non-relativistic limit. Now, everything is very definite. I'm going to place a coordinate system. I know where is the origin, and I can easily trace out that okay, this is the position vector of this particle mass m having some velocity, and whatever I can easily find out, calculate if it is in constant force, right? I can easily know what would be the equation of motion. X is equal to ut plus half at square, right? V is equal to u plus at. I can understand what about the velocity, and then you know that what is v square is equal to u square plus 2s and so on, considering that there is a force acting on it, but force is going to be constant, a uniform force, right? Very good. And I told you that we have already worked out that okay, you don't have to know anything about the force. You can just either use the Hamilton formalism, define the kinetic energy, define the momentum and the potential and the interaction. If the particle is free, therefore interaction goes to 0. And if the particle is in some kind of a force, some kind of interaction is there, then therefore you have some kind of potential, and you can find out the equation of motion by taking the derivative like del h by del p, del h by del x, right? And from there you can easily find out the equation of motion. Okay, I have a very good understanding that if the classical particle is there, I know what would be the equation of motion, right? If I am just bounding this particle inside a box, I exactly know what would be this particle. But let's take a moment. I want to actually observe this object. How do I actually observe this object? The observation is very simple. You see that if you are sitting in a dark room, if you are sitting in a dark room or place any particle in a dark room, you are not able to see it, right? Can you able to see? No. How we can see this particle? We can only see the particle if we light up it. Light it up. Light it up. That is how we are going to see it. Because we understand that if something is in dark room, no light is coming from it, therefore I am not able to see it. If I am not able to see it, I am not able to observe it. Although I can say that, okay, there is our equations which is going to tell you that if there is no force applied to it, I exactly know what would be the equation of motion of this one. But let's say that I want to actually do an experiment to try to figure it out, therefore I have to light it up, and you say that, okay, I'm going to apply some kind of a constant force and I will to see that, okay, where it should be. Let's say that it is a dark room. I have to give some kind of light, or I have to remove the walls and see that, okay, where it is, and everywhere I am going to mark the grids inside a box. And after some time you will see that, okay, this particle is over here at this moment, this particle would be over there at this moment, right? So it is a very simple thing that I have to light it up, and from this lighting up it will bounce back to us, and we can exactly see what is going to happen with this object. And although if I am not lighting up, my equations are very sufficient that will exactly tell me that, okay, at what moment what happens to this object mass m. That is very good. Now let's make this object small. Let's take my particle very small, mass m. Now it is ball. Let's take it to this level, 10 to the power, let us say, minus 18 meter. Consider it to be an electron. Now I'm putting an electron in a box, right? 0 to L, there is an electron in the box. You see a very important thing over. Let us say L is your 1 centimeter or anything. Maybe it is in 1 centimeter, maybe it is in 10 to minus 10 centimeter. Whatever you want to assume, you can assume. You see over here that when I am placing an electron in this box, the size is extremely small. Imagine it that if you are being an electron, how vast this space will be. Somebody will tell you that, okay, what would be the dynamics? You say that, okay, since electron is a mass, electron is a particle, and obviously it will have some kind of mass, I exactly know what is the coordinate of this particle inside the box at any particular time, right? It's very interesting that I know. Now since there is no any, if you apply any force of gravity, it is not going to feel it, because the force of gravity is enormously small than whatever it will experience. Therefore it's kind of weaker force, and hence there is no acceleration. I can just simply say that, okay, x is equal to ut. So given the velocity of this electron, I exactly know what would be the location. Very good. You know what is the location, right? At some time, what is this, where the object will be. Now I am saying that, okay, how do you know this electron would be there, right? That is one of the valid question, is that how do we know, since nobody has seen the electron, you don't have the capacity, you don't have that kind of resolution that can tell you that, okay, where is this where the electron would be. And then you may say that, okay, I will apply some electric field and magnetic field, and the way that Thomson has done the experiment, I will do. But I'm talking about here, see, this electron is somehow there. There's only one electron, correct? It's just only one electron is there. You don't have any stream of electrons, and you are not applying any kind of force or so on and so forth, and nothing else. So how do we actually know? So you say that, okay, since we are doing a thought experiment, what we can just do is that, okay, we can just take and make some kind of grid. This is how we are going to understand the location of this electron. But when I have plotted this grid, you see that this grid has particular length, right? when I'm plotting this ink in the board, you see that the length or the width of this ink is 10 to the power minus 6 meter and so on, correct? Now compared to this length, it's 10 to the power minus 18. It's way smaller than it. So you see that, okay, I have to then zoom in. Now when you will zoom in 10 to the power minus 6, it looks very huge. But when you further zoom in, let us say 10 to the power minus 10 meters, you will actually see the atoms in which these things are actually, the array of atoms you can see. But still you are 10 to the minus 10 meters or 10 to the minus 12 meters. Now as you will go again inside it, because you are placing an electron, then you have to, in order to locate the electron, actually you have to, probe it deeper and deeper and deeper and deeper. And when you are going a little bit, more deeper, now you are inside the atom. So the array of atom is now gone. You are seeing this line because there are array of atoms or molecules, and that's how you are seeing, you are actually seeing that some kind of structure. But when you go at the atomic level or beyond atomic level, there is no structure. There is no definite structure. What you can encounter is just like, something there, you cannot imagine it. Let's say that you are inside an atom, and inside an atom there is no any structure. It's completely different. So there is no line now. Great. So line is a manifestation of some kind of atoms arrangement that you are seeing classically. Great. So if there is no grid system exist at the atomic level or beyond atomic level, how do I locate it? Classically, I can locate it, right? Classically, I know where would be the ball because ball has some definite dimensions, right? But over here, I don't have any definite dimension over here because electron is far smaller than the way I have plotted my grid. So you see that, okay, what I can just do is that, okay, can I do something? Can I use some light, some laser? Somehow make a grid of lasers, and then I will able to, somehow locate the electron. Well, very good. You want to use some light because eventually I have to see the electron. And I say that, okay, if I fire up the light, then the light will, at the moment when it will, interact with it, it will again bounce back to us and I will see the electron. Correct? This is how we are actually seeing it. Classically, we are seeing the object like this, isn't it? That something has to be interact. Well, since your object, that is electron, is extremely small, right? Dimension of electron is 10 to the minus 18, right? Therefore, the light that you are going to project, and let's say the light is a wave or maybe a particle, because you already understand that, okay, light is made up of photons and so on. Let's say that we are taking that into account. It is going to hit it, the electron. But if I just do a simple calculation, because let's say that, okay, this is the dimension we are talking about, it's basically a wavelength, then I can easily calculate the energy corresponding to it, Sc over lambda for the photons, right? So let's say that in order to probe this electron, the dimension of the photon must be kind of same order of this electron. Then only you can hit the electron and say that, okay, because you have this idea like that, okay, there is a ball, I have to actually hit it by some smaller thing in order to get it, okay, where in order to locate the every particle of this one. If I am going to hit it with a very bigger thing, I am not able to probe it. Therefore I have to hit it very smaller wavelength. So the more the smaller wavelength, higher the energy. So whatever the electron would have some energy, the energy of which I am going to hit the photon, it's enormously big, right? And if I just plug it hc over lambda, let us say lambda is again 10 to the minus 18 or 10 to the minus, let's say that 10 or something, whatever, you will get that the energy that is coming out to be 10 to the power 10 electron volt. It's very huge. So in my thought experiment, I take an electron in a box and I want to locate this electron inside the box. And to do that, I am using the same way, same analogy, that I am seeing an object. I am seeing a classical object, right? So when I throw a light beam to this electron to locate, okay, where is this electron now? I am seeing that in order to probe it, the wavelength of the photon must be of this electron. But if I try to hit this photon, the photon has enormous amount of energy, and this enormous amount of energy can give the enormous amount of kinetic energy to this electron. So electron was, before, let us say that it was relaxing, it has some kind of velocity. I don't know what is the location, but if I want to probe its location or any information I want to get it, that okay, what would be its structure, by hitting a photon of the similar dimension of photon, then I have actually provided enormous amount of kinetic energy to this electron, and now electron has disrupted, it has gone wild. So what kind of information I'm going to get? One thing we have to understand first, that okay, if I want to measure some quantum particle or any particle, I have to throw a light or any other mean, maybe some series of electron and so on, right? And then this thing has to interact with that prey, right? And then it will come to us by taking some information from it. But this interaction must be lighter, so that it does not disturb its kind of state. Because if it was at some other state and now light is going there, it will completely transfer a lot of energy, and it has disrupted so many things, of so many informations. Therefore light is not going to carry a good information, right? Are you understanding my point? Therefore the measurement, okay, then I will take that, okay, I have to just somehow reduce it. Therefore my wavelength would be more, some kind of a comparable, but I am not going to get a lot of information, because the way I am going to measure it, it's going to disturb my electron, and it will change its state. State now means that whatever the initial state it was, because of this interaction, it's going to disturb every time whenever we are going to attempt any measurement, right? Unlike classical mechanics, what I observe is that, unlike the classical mechanics, when I take a measurement, there is no any disturbance of state. But when I attempt to measure a quantum particle, the act of measurement can disturb its state. So if I just throw a light one time, I am not going to able to get information. Obviously I am not able to get complete information, because it has already disturbed it. But now I have to do this process for many times. So one thing I understand from this little thought experiment is that, in order to understand the dynamics of a quantum particle, you have to repeat your experiment many times. And then if you want to, let us say, measure your position, you have to make it, let us say, x1, x2, x3, maybe lot of time, and then you have to average this out. It means that the quantity that we want to measure for the quantum particle, we have to repeat it many times, and therefore we need to take into the statistical, we need to take statistics into our account, because one measurement is not going to enough. We have to do the experiment many times in order to validate the result. Okay, that is what we can think of. And since it is all the time will create a new state, or obviously the way you are going to measure it, it has disturbed the particle, and hence the information that you are going to get is not 100% accurate, right? Therefore, one thing is now completely different from the classical. When you have the definite description of a particle or if state in classical mechanics, the description would become vague over here for the quantum particle, because you have to take a measurement, and at the act of measurement will obviously disturb the particle, and then you have to take into account statistics, and whatever you are going to measure, you have to take an average quantity. That is now clear. And one thing is also clear. I cannot simply consider this quantum particle as some kind of a particle. Because according to classical mechanics, a particle will have definite position, definite momentum, right? On the other hand, when we say that, okay, this is the classical picture, but when I translate it to quantum particles, this thing changes. Because over here we understand that in quantum mechanics, there is no role of reference system. There is nothing like reference system, because there is nothing exists like array of elements that will give you a kind of, idea, kind of effect that, okay, there exists some kind of line. So there is nothing. So there is no reference system exist in the quantum level. The first thing is clear. Now, when there is no reference system exist, classically what we think is that, we have the 3 degrees of freedom. These 3 spatial degrees of freedom, either we can go left and right, up and down, forward and backward. Because we have some kind of manifestation that, okay, these are the only movement is possible. But it's not there for the electron. Because electron is the tiniest particle. There is no structure there. Therefore, the way you think of this 3-dimensional world, the Euclidean reference system, right, is not there. So one additional thing, it is clear that, if you want to understand this quantum description, you have to throw away this Euclidean dimension, Euclidean, cubic coordinate system, because there is no coordinate system, anything. So I have to devise a function, first of all, function that can have degrees of freedom. And these degrees of freedom, let us say that, okay, it will have some time, obviously, because still at the quantum level, we don't know what is time is. But there is no Euclidean dimension, but let us say that it has some spatial degrees of freedom. And I am not saying that this XYZ actually representing your Euclidean dimension. There is nothing like Euclidean dimension. These you can just refer to as a spatial dimensions or degrees of freedom that this particle can have. One other thing is that particle description is not going to work, because particle description requires the validity of the position, this momentum and so on. But we don't know if I place an electron, it has some velocity, but I don't know any of it because I have not yet measured it. And any return of my measurement, it will give its new feature. So therefore the particle description is not going to work, right? So I say that if an electron can go from this point to this point only by this base trajectory, the concept of trajectory is not going to work over here, because it's not a particle. When I just label something a particle, I know from a classical mechanics have some definite type of trajectory. It can have definite trajectory. So we say that electron is over here, electron will over there, having some specific trajectory. No, it can go anywhere. Nobody has stopped it. So I don't know what would be the possible trajectory, or you can say that there could be billions of possibilities. And since I told you that there is no reference system, therefore there is no concept of trajectory there. No reference system, nothing trajectory. So you have to throw away this description. So now you can see from our thought experiment what we have to throw away. So now, all right, I don't have any particle description. Then how can I understand anything about this electron? Well, you see that I have another description in which, classically we understand something. That is called wave. Now you may just say that, okay, because you know what is wave function, that's how you are actually taking the wave. Well, obviously you have to try something out, because as you understand that you know the particle description will not work, therefore I have to adapt something. Now why I'm adapting only wave? Because again, wave, how the wave is generating? You see that if you have a system, a spring and mass attached to it, and let us say you have given some kind of x, some kind of disturbance, therefore I z in x double dot is equal to minus of kx with m, this one, right? So this is basically a Hooke's law for the spring with having constant k, and x double dot is d2x over dt square, the time derivative, right? Now you see that if you want to follow, if you want to, describe, find out the solution of this x, it's coming out to be like a of sine omega into t. So it basically tell you that it will actually, it is not a wave, it's just tell you that, okay, it will having some kind of an oscillation because your x is changing with time and it simply oscillates. Now, so if I have some object that is oscillating, it actually give me some kind of a glimpse of a wave, right? Because it's actually repeating it. In repeating, it means its position is changing. It's basically oscillating. So let us say that I have a many these particles that is vibrating, right? So let's say that it is vibrating, and therefore it will going up and down, up and down, up and down, up and down, and it will generate some kind of wave. Because that is what happens with a string. Let us say you take a guitar and you plug this string, then what you will manifest is that the string will generate some kind of wave, or maybe this kind of wave, or maybe this wave, right? So how this wave is generating? Because this every particle on this string is going to vibrate, and this vibrating is actually create some wave. So what is the basic thing? The basic thing is there's harmonic oscillators, right? These oscillators, a mass is attached with the spring, but if you just put it many vibrating masses, these vibrating masses will manifestation of the wave. So if I have this wave, I know the particles are vibrating. So classically the wave is generating because of the many vibrations that is taking place, many vibrations in form of this particle. Now that is the same thing that is happening with the crystal. In the crystal there are array of atoms, and if you have taken any courses on thermodynamics, you have seen that people have tried to model, try to understanding that, okay, how the energy levels are actually coming for different crystals. They are saying that, okay, all the atoms are plugged with some kind of spring and they are vibrating, and hence they are producing some kind of wave, right? So over here, I'm saying that, okay, either you consider a particle as just a particle, definite particle, or you may just say that, okay, in classically, we have another description that particle is there, but it's kind of vibrating. It is not sitting there, because if it is sitting there, there is no wave. But when you have some kind of vibration, it can manifestation of a wave, right? So if I just say this problem right over here, that, okay, I have a string and consider a little bit of the string, okay? Let's say that this is a portion of a spring, and at this portion there is x1, and this is the portion where x2, and when you have giving some kind of a tension, let us say this is the tension t1 and this is the tension t2, I can always decompose it in these directions. Okay, let us say it is theta 1 is theta 2, therefore I got t2 cos theta 2, t2 sin theta 2, t1 sin theta 1, t1 cos theta 1. Now you see that if it is in equilibrium, these tensions are going to be equated. T1 cos theta 1, right, is equal to T2 cos theta 2. T1 sin theta 1, T2 sin theta 2. But when you are disturbing it from the equilibrium, therefore obviously there are two different forces acting on x direction as well as y direction, right? So let us say that, okay, this is the x direction, you want to vibrate in the y direction, right? So you have, let us say, I can consider that there will be some net force on this y direction, and in the y direction I can simply say that, okay, what is the direction in y? This one. Let's say that, okay, we have sine theta 1 minus t2 sine theta 2, and this will basically give you the net force on y. But the thing is that this displacement is enormously small. Let us say theta 1 minus theta 2, whatever the displacement you are going to give, is very small, and hence theta 1 is approximately 0. Sine theta 1 could be written as in terms of tan theta 1, correct? So Fy would become T1 tan theta 1 minus T2 tan theta 2, isn't it? Well, now theta 1, if you know in x and y, if you have some curve, then this tan theta 1 or tan theta is basically tell you the slope of this curve, and this slope is basically dy by dx. So I can say that, okay, there is a wave that is generating in this string because of manifestation of the vibrations, and this wave, let's say, it shows the displacement of the particle in the y direction. I can just say that, okay, that will become delta psi 1 by delta x, t2 delta psi over delta x. Over here I can just say that, okay, x is equal to x1 and x is equal to, let us say, x2, and whatever you want to use, no problem. Now I can just simply say that, okay, these are basically f of x1, and let's say that this is f of x2. And considering that since x1 and x2 are very, the difference is extremely small, x1 minus x2, let's say that it is delta x, and delta x is actually 0. Therefore, I want to understand that, okay, how this dynamics is going to play. I can use the Taylor series expansion around this point x2. So I must say that, okay, fx1 at around point x2 using Taylor series expansion. So it would become simply fx2 plus delta f over delta x at x is equal to x2, x1 minus x2. Again, simply del f over del x square, x1 minus x2 whole square at x is equal to x2. This is the Taylor series of this function, right? Considering that del psi over del x is f of x1, and these are two derivatives at different point, I am just saying that, okay, whatever the function I am taking, let's expand it around x2 because these points are very nearby to each other. Then see what happens. I immediately get that, okay, fx1 minus fx of x2 is delta f over delta x1, but it will become what? Del 2 by del 2 psi over del x square at x is equal to x2, and this is delta x, basically delta x, right? And this would be triple derivative, and x1 minus x2 is already small. Any square would become lesser quantity. Therefore I can simply say that, okay, I don't require you, and hence I have this important relationship like fy would become f of x1 minus f of x2. The tension is basically same, right? Over here, whatever tension that is acting on it at T1 and T2, they have to be same, and therefore it will be del 2 psi over del x square at x is equal to x2 into delta x. Now this is the net force that is happening because of when we have given some kind of a disturbance. Now we understand that, okay, this Fy is basically what? The mass times acceleration, right? Now we can define another quantity there because we are talking about the string, and string have some mass of the string, and I can define a quantity called density, mass over length, isn't it? Mass over length is basically what? Mass per unit length. So if I have taken this small section of the string, therefore this becomes m over delta x. Delta m over delta x would be mu because the density is not going to be changed. Since I am basically seeing in the very small region, right? Therefore Fy would become mass. This is, let us say, called delta m, and the density, and in which direction you have some acceleration. The acceleration in this direction, basically it will govern by delta psi by delta t square, right? Is equal to t times delta x d2 psi over delta x square. Now I can simply write it over here. Delta m as mu delta x delta t over delta psi t square is t delta x del 2 psi over delta x square. And now delta x cancel out. I have this equation that is basically telling you the wave that is generating in the string due to the vibration of its molecules or its particles. And this is called the wave equation that is developing in the string. And it is very interesting. And this guy is called tensor per unit mass, whatever you can just say that. And this should become simply proportional to velocity square for this case. So delta 2 psi over delta t square is equal to v square del 2 psi over delta t square. Sorry, delta x square. So what is the description we have used? I have used that wave can play a description of alternate description of the particle, because wave is generating when particles are vibrating, and because of these vibrations we can have the effect called the waves. But the question again come to our mind that how we can actually find out what is this function f, because ultimately the role is that we have to find out this object. Otherwise, because we say that okay, this object is taking all the information of the quantum particle, so what kind of equations that is basically giving the restriction on this f, that okay, this f will have this particular information, or this is the information that it will going to contain. All right, this equation is actually giving you the classical wave equation. Now first of all, if I have a string between 0 to length L, right, let us say that massless spring having very little mass, right, is between 0 to L, and if I want to disturb it, then I have the following, but how we can know that how the wave equation will look like. Now in order to solve this equation, you have to must understand that this is the second order differential equation, and then this is also partial derivative equation, right? Now psi over here containing the information regarding x and t, now it is this psi is just this classical wave equation, and since it is it's kind of tell you that how the disturbance is actually generating, and this disturbance is kind of a wave, therefore it has to follow some boundary conditions. And the boundary condition, it says that okay, at any time when x is equal to 0 and at any time when x is equal to L, the disturbance is going to vanish, right? As we understand that there is no disturbance at these endpoints. Very good. Now this is called the boundary value problem at boundary. Now about another equation is that, all right, when we have anything x and at any time, let us say t is equal to 0 time, we have certain function, let us say some function called h of x is there, right, at t is equal to 0. But I don't know what happens to t is equal to t time. I just take a derivative, because these are the second order differential equation, and therefore it requires the initial conditions. Either you just assume you know what happens in the boundary, or you know what happens at t is equal to 0, and we say that okay, I also know what is the first derivative of this psi with respect to t, and let's say that this becomes g of x. And the problem is that we want to solve this equation, and how we can solve this partial differential equation? Well, in order to solve the partial differential equation, we can just simply say that okay, there is a two separate function, one is depending on x, and there is a time function that depends on only time t, right? So once I will incorporate it, I understand that del 2 psi over del t square will just give you the time derivative t double dot. Del 2 psi over del x square will give you the derivative, let us say derivative with respect to x, and there is no time t. So this dxx is actually telling you d2 over dx square operating on psi. Psi is this one, and since it is partial derivative equation, therefore these two quantities are independent to each other, right? Now I am going to just put it over here, d2 psi x t double dot xt double dot is equal to t delta x with v square. And once we have written this equation, I am considering that, okay, there is something is equal to, let's say, minus of e, some constant e. And if I just use this equation, I can simply say that t double dot by t times v square is equal to minus of e. And similarly, I can say that delta x over x is equal to minus of e. And I can simply say it's multiplying by ex, and this guy will become d2x over dx square, and this has the same equation as equation of simple harmonic motion. That's why I have chosen this minus of e, since I have to understand what would be the solution of this equation. And once I am feeding it, I know exactly what would be the solution. X would become, let us say, sine. This would be square root of e, as you understood, and x c2 cos square root of e. Now these c1 and c2 are constant because there appear two constants because the order of derivative is 2, and hence two initial conditions are required to actually find out what are these. X in the spatial system, I have two boundary conditions, right? At x is equal to 0 and x is equal to L. So it simply says that, okay, x goes to 0, it has to be 0. Therefore, whenever x is there, just put it x is equal to 0, this guy will gone, and you got c2. So c2 becomes 0. Similarly, x at L would become c1. c2 is already there, therefore it's already vanishes, c1 sine root e, and therefore this is L. And this x of L also vanishes, right? The disturbance is going to vanishes at these boundaries. And now c1 would be gone, and we got root el. And now tell me when sine becomes 0. Sine becomes 0 when sine of the argument takes 0 degree, pi, 2 pi, 3 pi, 4 pi. Therefore, I can just write it over here 2n pi, right? It means the n is just integer numbers, n could be 0, 1, 2, 3, and we can get our solution. So sine is there, therefore arguments is going to be taken like this, or sorry, not 2n pi, it's only n pi. It will become simply n into pi, and therefore I already know what is the e. E is basically n pi by L, or e square becomes n square pi square by L squared. Therefore, I know exactly what is the solution of x. The solution is, because I don't know how to determine c1, well, c1 should be there, sine e square, take it as square root n pi over L into x. This is the how spatially your distribution or the wave function will look like. This is the spatial wave function, right? The how waves is generating or wave propagating in the spatial direction. On the other hand, here is the function that dictates on how the t will look like. And similarly, I can say that, okay, there will be something like c2 cos, this would be e, and there is v, and there is t, right? Not c2, it has to c3, and c4 sine root e, v, and t. So I know what is the solution of t. Now I can write the wave function as x comma t is equal to c3 cos root e, I know what is this, n pi v over L into t plus c4 sine n pi v over L into t, right? And multiply by, because psi is this t times x, and hence I can simply write over here sine n pi over L into x. Now why I'm writing this one? Where is the c1? Since there are already two constants, therefore I can absorb it there, right? Now I can use the other initial conditions, right? Let's say that what happens at t is equal to 0. When t is equal to 0, I got something like h of x is equal to, when t is equal to 0, there is only c3, and c4 is already gone, and I got over here sine n pi over L into x, correct? Now using the Fourier transformation or so on, I can write over here C3 becomes 0 to L h of x sine n pi by L into x, and this will become 2 by L. So this is how now we found out what is C3. Now another thing I can get by using taking the time derivative, d psi over dt. So this cos would become sine and t is equal to 0, this vanishes. This sine would become cos and t is equal to 0, this will be there. So this will become C4 n by v over L. This is cos n pi L into Vt, and another thing is that n pi over L into x. Now at t is equal to 0, I have to make sure that has to be t is equal to 0. I got only, let us say it is g of x I have considered, n pi by L into V, cos is 1, this is n pi over L into x. Now how we can determine C4? C4 is now becoming pi V over L, or become 2 by L, 0 to L, g of x sine n pi over L into x dx, right? Now I can simply figure it out. This one L get cancel out, 2 by n pi into V, 0 to L, g of x sine n pi over L x into dx. But now we have calculated what is this C3 and C4. When we are going to plug it in, I exactly know how the wave equation will look like. So wave equation has two important things. One is how the time will evolve, and it says that okay, this has certain things sine n pi L over x. So when n is equal to 0, it's equal to 0, right? There is no nodes. When n is equal to 1, you can have different nodes and different shapes are going to be there, and therefore we understand that this wave equation that we have generated is actually telling us that any disturbance will give you the behave like a wave type of behavior, isn't it? So it's kind of very interesting that a particle vibrations can lead to the wave, but we must have to understand that okay, the string is just remain the string, correct? And any vibrations can just generate a wave, and this wave can be calculated by providing certain boundary conditions, and we have found out that what would be the wave and so on and so forth. So if you have already understood that okay, how the quantum mechanical, if you put a particle in a box, then how the solution will look like, so you have some kind of flavor that okay, the solution is kind of matching, but it is far from the ending. So now we have understood that okay, this equation will help to identify the wave function, but again the question is that it's a kind of a classical wave and generating on a string. But let us say that if a quantum particle has to move from point A to point B, I don't have any description where it will just say, I can say that okay, it will follow some path, right? Although it has it can have some dynamical freedom. Let us say that I have certain information of particle or electron over here, and it has degrees of freedom, right, x and t. How it will reach it, I don't know anything about it. So we can just simply say that all right, since you don't know how it can take place, so this is, let's say that this has all the information that is required, right? So let's say that this psi x of t is there, correct? Now we can simply think of it as like that at every instant, maybe in every way, before it is reaching to point B, right, there could be many configurations in which the informations is encoded over here, this psi, right? So let us say the electron is over here, maybe over here, maybe over here, maybe over here, right? So each and everywhere the electron can be, it will have some kind of state, right? These are basically some kind of state, and they have certain informations. And we say that okay, we can just take that there could be some infinite configuration in which our electron can be there. So let's say that okay, and this is the grand function that is going to build up on these informations, right? So psi of xt have all the informations about the electron, right? Now it is reaching the point B, and before reaching the point B, electron could be anywhere, and hence at any point it would have some kind of information that would be a little bit different than other, and then other, and other, and other. So I can just divide it into infinite wave functions, or let's say that it is just like infinite. Okay, this is not x, this is x. Look, I already told you that there is nothing, no meaning of x1, x2, x3, and so on. Basically I'm telling you that this psi is different than this psi1, psi2, psi3, psi4, psi5, and so on and so forth. There could be infinite many states before the electron is reaching at any point. I don't know anything about it, and I am saying that this x and t are just dictating the degrees of freedom at any point it has. Now one very key interesting thing is that this is actually written in terms of a superposition principle, just like we have followed with the forces, electric field, and so on. That electric field is having the superposition states like e1, e2, e3, and vectorial you can add. Over here, these are the information, these are the objects that have the information at different instants. How the electron has reached, it has the psi xt is actually built upon these informations that it has, right? Now it has the same structure, like let us say that you have any vector in a three-dimensional space, a classical object. I can just write that any component in the x direction, any component in the y direction, any component in the z direction, correct? So if I have some kind of matrix, then I will write it as 1 0 0, a2 as 0 1 0, a3 as 0 0 1. So basically this A, that is containing everything, every information of the classical particle around the three-dimensional space, I will have this column vector A2, A1, A2, A3. So this is some kind of a state of an object when we are dealing with classically. So similarly, this psi is carrying the information encoded in this column vector having the infinite dimensional state. And this will actually lead you to Hilbert space, but I am not taking any kind of name and so on. So they have the same analogy. Over here we are restricted to this spatial direction. Over there is no restriction. It has some information encoded in these objects. Now according to Cartesian coordinate, we got x dot and y dot is 0. So these are mutually perpendicular. Over here we say that each and every states are orthogonal to each other. Let us say that psi1 dot psi2 is going to give you 0. They have the unique information, right? These will have the unique information. So if you take some kind of dot product, what is the mean dot product, we're going to explore later. But this is how we can just say that each and every states of this quantum particle has to be orthogonal the way we are seeing it over here. That is how we are building up our intuition regarding this psi of xt, right? Now since I told you that the classical wave is just like a wave, therefore I have certain description of the wave, because as I told you that let's say a particle is doing SHM, or there is some kind of electric fields are also wave, so we have better understanding of wave. So I am considering that okay, let's say that a wave psi, we have devised that okay, a string is attached between 0 to L. Let us say that there is a wave that is freely moving. Then for a freely particle moving, we can write it as sine of, let us say, kx minus omega t and so on, or maybe a e to the power I kx minus omega t, right? The exponential, and we can discard the exponential one. Over here we say that okay, I have this description of wave e to the power I kx minus omega t, right? And let's say we do something as follows. This is the classical wave equation, plane wave equation, that is the formula of psi, right? Now de Broglie came and says that all the matter that have two following states, that it can have also a wave like behavior, right? And similarly, the Einstein came and shows that you take an photon depending on the how you measure, it can behave like a particle as well as a wave. And he proposed that each and every matter have the wavelength that is denoted by lambda is equal to h by p. That is called de Broglie wavelength. Now, for classical object, this wavelength is extremely low. Therefore, we are not, showing any kind of wavy characteristic. But quantum mechanically, this is, observable wave. On the other hand, Planck shows that E is obviously h times frequency, h times h bar, h by 2 pi into omega, right? E is equal to therefore h by omega, right? So I can just simply take it, right? K into x, omega is E over h bar into t. Now I am building a classical wave, trying to build some kind of quantum mechanical wave by introducing these following statements, by saying that what is the energy relationship between energy and frequency, and let's say that we have a de Broglie wavelength, right? Now we know that what is this, k is a wave number and it becomes 2 pi over lambda, and let me just write lambda as h by p, 2 pi over here h by p, right? So this becomes p by h bar, correct? So k becomes p by h bar. Therefore the psi in this case would become e to the power I, k becomes p over h bar into x, e over h bar into t. So it will simply becomes I over h bar px e into t, right? Now we know that, okay, this is a quantum mechanical type of wave, right? It's still a plane wave, but kind of a quantum mechanical one. I have this equation delta psi over delta t square is equal to v square delta psi over delta x square. Now plug this into it. Now since this is partial derivative equation, therefore it will only take the time derivative over here. So it simply becomes I by h bar minus e. If you do the second time derivative, again I by h bar minus e, and you are going to take the square and you are end up with same thing. Therefore I'm writing psi. I hope you understand how to take the derivative. Similarly, over here, I will have v square I by h bar, this is squared. Taking the x 2 times, it will end up with p squared. Now, if I do minus minus plus, I square becomes minus h by square, e square, this is psi will cancel out, v square by h bar square, p square. Minus minus, h cancelled. Now e square is proportional to v square p square, right? This is the energy of the wave. Now since I am in the non-relativistic limit, I know this is not true because we have this thing like energy is equal to kinetic energy plus potential energy. Let's just say it's a free particle, therefore kinetic energy would become p square by 2m. So this should not be e square, this should be only e, right? E cannot be equal to p square. Similarly, we have already know the Hamiltonian formalism. Hamiltonian will just tell you that p square by tm plus potential, and if the particle is free, potential is going to be 0. H is equal to p square by 2m, correct? So in both the cases, we have this form, not this form. So what should we do to get this one? So I say that we can just, there is no way, there is no fundamental way how you can derive this Schrodinger equation. So you have to use the heuristic method to actually find out that, okay, this could be the equation. That's why we have already done what is Hamiltonian and so on. And that is the intuition that is going to, work for us. So this is not going to work. Therefore, what I can simply say that, okay, the equation should look like this. Del psi over del t is equal to v square del 2 psi over del x square, because over here I got p square, but this side I need only 1e. Now if I do this one, I will get I by h bar with e minus e, right? Over here this is good. Now, if you do take a one derivative and another derivative, that is the interesting thing about exponential one, because it's remain the exponential, right? And over here I will get the same thing. What was it? V square I by h square, and it's negative V square by minus V square over h bar square, that is P square psi. Now everything is great. Negative negative will cancel out each other. H bar is gone. I is psi, let us say psi is gone. V square P square by h bar square, h bar psi. And I told you that this V is for the string, it is velocity, but nevertheless it's, you can treat it as some kind of a constant. But the problem is that over here it is complex. I have to remove this complex. So therefore what I can just simply say, why don't you just do this one, because you see this is energy and h is what, P square by 2m, and h in the case where things, well, let us say that your system is closed, h would become P. Therefore I have to remove this one. So V square is h bar. I have to remove this I, it should be multiplied by this one, and also this guy 2m, because I require also 2m. And hence I got IE is equal to I h bar over 2m P square psi. Incredibly good. And I cancel, and now, well, V square by, oh, therefore there was some h bar, right? This is basically P square by 2m. Psi is already gone. There was psi is now already gone. Oh god. I simply got E is equal to P square by 2m. So if I just compare it over here, del psi over del t, over here V square, I know what is this. V square is becoming I h bar over 2m, and this is basically del 2 over del x square is executing on psi. Now comparing it, I can simply say that, okay, I can just make this thing little bit good with I h bar. This becomes delta by del psi, and this is h squared by 2m del 2 over del x square psi. And you see over here, it's it like this, P square by 2m. So this E will eventually becoming what? So it simply says that, you know, whatever the E is your I h bar del by del t, and P square by 2m. So now comparing it at P square by 2m is equal to minus h square by 2m del 2 over del psi square, so del x square, right? And 2m cancel out. P becomes h bar I h bar del by del x. And you see over here, as I told you initially, that whenever the act of measuring is that, you know, something has to be, whatever you want to observe, that thing had to be act on that electron, or act on the quantum particle, and then it will take the information out from there. So it is like it's not like classical mechanism. Okay, some things go there, hit it, and then come by. It has to be, you know, interaction, and this act of interaction makes the, let us say you want to mix the observable, let us say you want to make your you want to measure the position, or you want to measure the momentum, it becomes operator. You see that del by del x is some kind of an operator that is going to act on your psi, right? So in the quantum mechanics, we are labeling it as a P bar. Similarly, E bar, E hat. So these guys show that these are not just your quantities. These are now becoming, if it is an observer, it has now becoming an operator, right? So if I'm writing h is equal to P square by 2m V, so in quantum mechanics, it would become h bar P bar square by 2m plus this potential operator. Now I will write it as I h bar del by del t. Now let us say it is acting on something, because I want to find out the energy. You see that h bar is corresponding to the energy. So h bar, when will act on this psi, it will give you information about the energy of that system. Now, if I have to go transition from classical to quantum, I don't know how the x and y look, x and momentum look like, but I know that if in classical mechanics we have the concept of energy, it does not care about that, whatever your intuition is, energy should be there. So energy should be there in the quantum particle. So I want to measure something. So this psi must, must return you the energy of that particle. What would be the energy of that particle, right? So h bar, h hat must act on psi, will give you the energy, and this energy is an operator which is equal to I h bar d by dt, and this energy bar is equivalent to h bar, right? And we have started with the free particle, but now we have already know that how the Hamiltonian looks like. I say that okay, I can have also interaction, and interaction will also act like this, and p square would become what? Minus h square by 2m del 2 by del x square on psi and v on psi. Now this has now become a Schrodinger equation. Is it correct? So what we have done so far, we have taken the classical wave equation. We found out that okay, just use a plane wave and use some quantum mechanical thing from de Broglie and Einstein, make a quantum mechanical wave which is free to move, not bounded by anything. We first of all make the relations little bit good, that okay, wave equation should be over here for non-relativistic case, right? And when we have fixed our equation, we use the Hamiltonian approach and saw that okay, how the p has changed. So now p has become a kind of operator. It is not like p what we were thought of in our case, right? Now p is now becoming derivative of x. Now you do not have to think of this x as the dimension of x that you are writing in the Euclidean system. It is just a spatial dimension that is a wave function will carry. It could be p, d, t, anything you want to say. So never think of it as the x from your point of view, right? It is just the x which has the spatial degrees of freedom. So now p has a derivative which has a spatial degree of freedom. Now you see that in classical wave, we were restricted our system that okay, I'm going to throw away anything which is coming with the complex quantity. But over here, we have understood that even the operator becoming the complex, energy has now becoming the complex. So, and psi for the simple wave is written in terms of e to the power I over h bar, and h bar is not zero, h bar is a quantity. So I cannot simply throw away anything. Therefore, the psi has become a complex quantity. In classical mechanics, we forbid the complex quantity, right? We say that complex are not observable. In quantum mechanics, these are completely a mathematical object. Do not try to visualize what is psi look like. No, psi has no feature. Psi has every mathematical feature. And from where you want to, capture the information. So psi is a complex object, and that is going to play a great role. But the question is that, okay, I know the wave function, and this is, let's say that, okay, quantum mechanical wave function. But the problem is that still, how do I know where is my particle? Right? Because in classical description, the particles, there are, many particles are vibrating and creating a wave. Now you say that, okay, in quantum mechanics, there is, only one particle. And say that this one quantum particle has a description of wave-like behavior. Whatever this is a quantum mechanical wave. But how do we know? So as we have the classical mechanics, there are a lot of particles that is vibrating in a space and time, creating the wave. In quantum mechanics, there is one wave, there one particle, whatever it may do. So if I have a wave function, it has some kind of an spreading in a space, right? Therefore, as we understand from the simple harmonic motion or whatever the wave will look like, that over here the vibration is small, then it is greater and greater. So this wave has amplitude, right? And depending on the intensity, we say that, these particles are, having the tremendous energy and so on. So I becomes what? Amplitude square. That is, this is amplitude of the wave, amplitude square. So I will tell you the intensity. I just tells you the intensity of the wave. The more the intensity, the more you can find that you can say that, okay, the finding the particle is huge. Now psi is a quantum wave function. It is complex. I need a real quantity, right? Again, because that is what we do, although it is a quantum object, but we need a real quantity. And since we have seen that, okay, intensity is a very important quantity because amplitude is there, but we need an intensity, that how intense the quantum amplitude is, because it will tell you that, okay, more the particle is there, more the vibration is there. Now since there is one particle, we say that, okay, the more the intensity I can, finding the particle in that particular region is going to be huge. Amplitude square, so how I'm going to square it? If I simply multiply it, I'm going to get a complex thing. So complex no makes sense. So what I can just simply say that, okay, amplitude, I need something which we can work with. So let's say that, okay, can we just take a complex conjugate? So you see that this is your wave function. You have to take your complex conjugate, because when you multiply it, the end result is a square minus a square plus b square. This is a real quantity. So over here, the definition of intensity would become the complex conjugate of the psi of this wave function. This is the wave function that we have. And this is the, again, these are mathematical objects. So these are completely mathematical definitions. You should not think of it, okay, what is this one? In quantum mechanics, when we will do, we will say that, okay, this is the dual of something. But now you understand that, okay, what we are. It's our description to actually understand where would be the particle. So this is the intensity. So let's say that in the box, if I put an electron is there. How do we know? The wave, whatever the wave will look like, it's there. I will say that, okay, there is a probability. I told you earlier that, if my act of measuring will disturb it, therefore I have to, I have to depend on the statistical technique. And if any quantity I want to measure, I have to take an average. Now, when we are saying that, okay, we don't know many information about it, we have to rely on something called probability, that, okay, this may happen, because there are a lot of information, it is not there. Information is like, okay, I can know about only 20%, maybe 30%, maybe 40%, right? In that case, what I cannot have any absolute number. Therefore, I will say that, okay, this intensity is nothing but probability. Take the wave function complex conjugate, and in this, either it has dx, dy, dz, whatever you want to say, right? As I told you that it has degrees of freedom, psi star psi. In the special degrees of freedom, you can just simply say that, okay, if this box is bound 0 to L, if it is unbound, or maybe in the universe, in the complete universe, you just put an electron and you can integrate it minus infinity to infinity. Or in the box, you just say that, okay, in the box I want to see that if the electron is there or not, the probability must be equal to 1. It ensures that the intensity must be there, that electron is there in somewhere in the box. At where, I don't know, but it must be there. So when probability says that it is equal to 1, it says that something is there, right? So you will have the chances to get the electron. It exists. And this is important. And in the quantum mechanical language, you can say that this is a normalization factor. Just like you have heads and tails. You take heads and tails, you say that, okay, what is the probability of head? It is basically 1/2. So probability of event is equal to probability of occurring that event by the total probability. So normalization is, it will say that what is the complete probability, right? And similarly, based on the probability, you can let us say that I want to measure something O. Whatever you are measuring, it would already become operator. As I told you, the momentum has now become an operator. And this bracket is actually telling you that you have to always rely on the average. I told you why. So now it will simply becoming, let us say 0 to L, psi star, this observer act on psi dx, right? And this will actually give you the, in quantum mechanical language, the expectation value of that. So whatever the thing, whatever the, as we understand the probability always lie between 0 to 1, correct? And therefore whatever the wave function that we want to create using this equation, now this is our governing equation, this psi, right? First of all, we want to make sure that this psi exists by normalizing it, and whatever the result you are going to get, you are always going to get between 0 to 1, isn't it? So the best thing about the differential equation is that, you see, you can say that, okay, you have assumed something, you have assumed that there is a plane wave and you have constructed a differential equation. Yes, that is the beauty of differential equation, that its solution is itself a differential equation. So let us say somebody has give you the solution, you can always make a differential equation out of that solution, right? So that is what we do. We have taken something, used the Hamiltonian concept and made the equation, and we call it, this is a Schrodinger equation. And now we have described everything, that what it should be the psi, what is the meaning of its state, right? It could have many configurations, and these configurations are encoded in the psi. Psi becomes psi 1, psi 2, psi 2. These are superposition states. We can say that, okay, it's not traveling or something, it has some information, like x, y, z are not the axes, they are just a degrees of freedom, correct? And yet we don't know how the time plays, therefore we have just say the time is just the parameter that is moving just like we think. But it may not be. Maybe in 100 years somebody will come and they will have a very better experiment, and they will say that, no, the time that you are thinking is not that time you are thinking, right? So if I am being a theoretical physicist, that is how we should think, that, okay, that is the meaning of wave function over here. And there are many concepts which I am going to understand from the perspective that I am a learner who wants a transition from classical to quantum. Okay, I have many information regarding classical, now I have fully gone to quantum, and now here you have realized that how things are, how things now become operated and so on. There is no discrepancy, although for me it is not discrepancy, because I know very well what is quantum mechanics and so on. But I have just used some kind of a vague interpretation. Some interpretation are not actually accurate, do not go with that. But this is how you have to understand, or at least I want to understand that, okay, how we can transition from classical to quantum mechanics without relying on any kind of experiment. Just I am a theoretical phase and I want to develop my own theory consistently, right? And in many lecture after, we are going to construct a relativistic version, but now we have fully gone towards the quantum mechanics, and the journey of quantum mechanics has now begun officially. And in the next lecture, I'm going to talk about the Hilbert space. As I told you that, okay, this has the same structure like the vector, therefore I'm going to talk about the vector spaces, the eigenvalues, what is the meaning of eigenvalues, so all the terminologies, but in a very simple way that you should not feel that, okay, you are doing something, right? So that is the idea. That's how I want to learn of physics, so that it should not feel something very strange. Okay, so I hope if you have any questions regarding this, you can just simply comment it down, and I'm going to take those questions in my next lecture. So we will meet in my next video. See you later. This is Dr. Saddam and Cap signing out.